Hello everyone. I appreciate your presence here today. My name is Hao and from the Hong Kong Polytechnic University, and it's my great honor to present our work titled Spatial Full Subnet for hearing aid processing. And for our solution, we just focus on the task 1, real ambisonic room impulse responses. And so for the previous CEC1 and CEC2 Clarity challenge, and the room impulse responses are simulated and then mixed with the audio sources and used for creating training and evaluation dataset. But for the current task 1, and it just rerun the previous CEC2 scenario, and but it introduces a new evaluation dataset and with the real impulse responses, which is measured using an ambisonic microphone array in the actual room. And so obviously, the aim is to access how well system trained on the simulated data generalized to unseen evaluation data with the real impulse responses. And in a hearing aid, and there are a lot of sub components. And for example, noise cancellation and hearing loss compensation and feedback cancellation and acoustic scene analysis. But for the clarity challenge, we just need to focus on the most important one, speech enhancement part. And for this part, the input is multi-channel input. So in specific, it is a 6-channel input. And for the output, and it could be binaural or it could be binaural output. So the binaural means it will output 2 channels, one for left ear and another for left ear. And for this task, and we needed to dereverberation, which means to remove the audio or the room effects, and to denoising and target speaker extraction to suppress the interference speakers and interference, the noise. And so now let us move on to the architecture of the proposed spatial full subnet. As shown in this figure, and we have many blocks, and in the upper part, we have an enrollment branch, which is used to determine which sound source is the desired sound source. And the input of this branch is an enrollment speech signal with a varying length. We feed this input into a pre-trained speaker verification model, and we use this model to improve the generalization to unseen speakers. And following this pre-trained model, and we have many stacked layers, such as multi-head attention layers and bidirectional gyro layers, and which are used to feed the output of the pre-trained model to our main branch. And in the main branch, and we input a 6-channel mixture signal and into our the full band and subband fusion model. And so we have integrated a technique, which is named frequency partitioning, and we will detail it later. And then we will do a inverse partitioning, inverse frequency partitioning and inverse short-time Fourier transform, and to obtain the enhanced signal. And finally, we have a hearing loss compensation module, and we just use the default NALR algorithm and to feed the output and to a specific hearing loss person. The proposed spatial full subnet is based on a model named full subnet, and as shown in its name, and full subnet is a fusion model and combining 2 types of neural networks. And the most innovation of a full subnet is to explore the advantages of the subband models. And this subband model process each partial frequency band or each frequency independently. And these models are rarely be used in conventional deep learning based methods, and are mostly used in the conventional signal processing algorithms, like beamforming or power density estimation algorithms. So why we want to use it? And so to know why we want to use the subband models, and the first thing is to find the background inside behind these models. And for full band models, it is easy to find that it can learn cross-band harmonic structures and long-distance frequency dependencies. And so for example, so as shown in this figure, and so we have a noise magnitude spectrogram, and only based on the higher frequency information, and for this first frames, and the full band model can very easily do speech enhancement. And so it may lack specificity. And let us explore the role of the subband model in speech enhancement. So with the aim of discriminating between speech and noise, the subband model is designed and expected to perform on the following grounds. And first, frequency-wise temporal involution of the short-time Fourier transform magnitude is informative, so due to the non-stationary nature of speech against the stationary nature of the most noise. And actually, so this is the foundation for the conventional noise estimators and so the speech enhancement algorithms. And so to illustrate this, so consider the figure. So we have a show so here, and on the left, so we have a noise magnitude spectrogram, and we just so extract a specific frequency band from this spectrogram, and as depicted on the right, and we can observe so distinct patterns, and the relatively stationary section, so maybe here, and it represent so might be so noise, and while the more non-stationary segments corresponding to speech. And so as for a subband feature, the input is so partial frequency or only a frequency, and it is very easy to distinguish between these two elements. And the second key advantage of subband models is the better acoustic generalization. And to better understand this benefit, and let us consider a typical scenario, and as shown in this figure. And so this is a standard recording room, and used to record or collect audio data and to train over neural networks. And in such an environment, the neural network will learn specific spectral patterns, so influenced by the microphone's acoustic response and the room acoustics. And well, so this is useful, and it also creates a challenge. And the network so tends to learn with this fixed pattern, so which can integrate its performance in unseen acoustic environment that exhibit new spectral characteristics. And so, however, and for the subband model, it operates differently, and by processing the noise input into a frequency-wise manner, and they break the dependency between frequencies. This means that the subband model does not overfit to the spectral patterns of a training environment, and is more adaptable when encounter new environments. So as a result, and the subband model demonstrates improved generalization. And this is evident in the table so presented here. And the black cell and indicate the model's performance when trained and tested on the same dataset. And the gray and white cells, however, shows the model's performance on two different unseen datasets respectively. And the performance metrics, so in these cells, suggest that so the final one is a subband-based model, and the first three one is a full-band model. And the performance metrics in these cells suggest that the subband model retain its effectiveness, so even when applied to new unseen acoustic environment. And thirdly, and an avoidable aspect of a recorded audio signal is the presence of reverberation, and to a certain degree. And the reverberation occurs when sound wave reflect off surfaces and objects within a room environment, and with different materials affects the sound wave differently across the frequency spectrum. And for example, so lower frequency wave, so with its larger so wavelengths, tend to bypass small object and are less likely to be absorbed, and resulting in a more pronounced reverberation effect. And high frequency waves, on the other hand, have shorter wavelengths and are more so readily absorbed or scattered by obscures, and leading a more complex reverberation pattern at these frequencies. And the frequency-dependent nature of reverberation is something that subband model inherently mimic, and by processing audio signal in a frequency-wise manner, subband model naturally align with the way reverberation across different frequencies. Given that reverberation is a common phenomenon in real-life audio environment, so ranging from small rooms or large halls, and the ability of a subband model to modeling reverberation effectively is a significant advantage. And so except for the frequency-wise stationarity and acoustic generalization, reverberation modeling, and so for the subband model, and there exists another characteristic, spatial characteristic. And so as shown in this figure, and so we have a microphone array, and with 6 microphone, and so we have a target sound source, and so we call it point sound source, and so for these 6 microphones, so they will receive the target sound source, and so however, and for each microphone, and they will receive almost similar, almost the same signals. So the only difference is the time delay and little energy decay. Okay, so and it means that so for these microphones, so they have a very similar interchannel. They have a very high interchannel coherence. And however, and for the diffusion noise and the later part of reverberation, and as shown in this figure, so this is extracted from this paper, and for the diffusion noise and the later part of reverberation, and so their interchannel coherence follow a fixed pattern, and it is large and for small arrays and low frequencies, and so it increases with microphone distance and frequencies. And however, so obviously, the subband models lose the global information and cannot model long-distance frequency dependencies. And so to integrate the advantages of both full-band model and subband model, and in our previous work, and we proposed this full subnet architecture, and the input is a magnitude spectral, and which is first processed by a full-band model, and the full-band model is used to capture the global information, and then subband model will process the noise magnitude spectral in a frequency-wise manner, and each subband model comprises a current time frequency point and its adjacent time frequency point, and to integrate the full-band information, we will stack the subband input with the counterpart of the output of the full-band model. And however, so the drawback of the full subnet is the computational cost, and because it processes each frequency at the same frequency granularity, and so one by one, and to process them. And this approach contrasts with the human auditory system, which is more sensitive and to the lower part frequencies, and more sensitive and less sensitive to higher frequency sound. And so to address this and to adapt our full subnet model to Clarity challenge, and we do a lot of modification. And so first, we introduce a frequency partitioning technique. So this approach apply different processing granularity across the frequency bands, mirroring the human auditory systems. And so as shown in this figure, and so we have a mixture input, and we use short-time Fourier transform to transform it from time domain to frequency domain, and then we will split all frequencies into several subparts. And for the lower frequency, and we will use a fire processing granularity, and it may process using a frequency by frequency manner. And for the higher part, we will process several parts, several frequency at once. And so in this way, we can apply different processing granularity across the frequency bands. And then we do a inverse frequency partitioning, and then do inverse short-time Fourier transform, and to convert back to the time domain signal. And so in our neural network, So we just stacked several full band blocks and subband blocks. And for the full band blocks, and we just made a COM1D block and to communicate the frequencies. And for the subband block, and we will process each subband unit independently. And to extract the desired sound source, and we introduce an enrollment branch, and so we use a pre-trained speaker verification model, and in specific, so the name is VNet speaker ResNet 34, and this is a 34 layer ResNet and pre-trained on work-scalable dataset. And then following this model, and we use multi-head attention layers and bidirectional gyro layers, and to try to fit this feature into our main block. And we use a combined loss function, and the first one is a multi-resolution short-time Fourier transform loss function, and as shown in this equation. And so this one represents the short-time Fourier transform magnitudes, and n is the number of elements in the spectrogram, and m denotes the sum of the short-time Fourier transform losses with different analysis parameters. And so except for this one, we also combine this multi-resolution short-time Fourier transform loss function with this time domain loss function. So in specific, this is a skew invariant SDR loss function, and we combine them together. And to train our model, except for the official 6,000 things, we also add an additional 20,000 things using the official CEC2 simulator. And we resampled all audio signal to 24,000 Hertz. And so finally, we obtain a model, and with a computational cost, about 145 G, and for each year, and for a 1 second signal. And so to train this model, actually, we have integrated a lot of advanced techniques, like fully shared data parallel and activation checkpointing, and to make use of GPU memory effectively. And finally, the model parameters is 13 million. And so now let us move on to the experimental result. And so we have evaluated our system on the task 1 development dataset. And so we compared the proposed system using 4 metrics: SSTR, PSQ, STOI, and HASP score. And the first row shows the performance of the unprocessed system, unprocessed audio. And so we can find that the audio quality is very bad. And the second row shows the proposed spatial full subnet system. And so if without additional things, and the performance will decrease drastically. And this is the provisional CEC3 listening test result. And although this is the provisional result, but it shows that the proposed system has drastically improved the performance. And in the future, and we will try to further reduce computational cost by using advanced techniques, like knowledge distillation or other compression techniques. And during our development, we found that after using the conventional fitting algorithm, like NARR algorithm, and the artifacts and the residual noise made by audio enhancement model will be further amplified. And in the future, we will try to find a way to distinguish the soft speech sound, and residual noise. And finally, in the future, we will try to build a surrogate targets for hearing loss compensation, as the current audio enhancement model and hearing loss compensation algorithms are separated, and we will try to build a end-to-end pipeline and to do this hearing aid processing. Okay, so the ball is all, and thank you so much.